I'm Anusha. I'm a principal software engineer with AWS. I'm with the AWS Messaging and Streaming organization. And today I'm excited to introduce our customer who's going to be talking about how they modernize their data streaming architecture using AWS. We have Jaewon Lee, who is the head of Samsung SmartThings cloud engineering team, doing a session for us today. You know, one of my favorite parts of being an engineer at AWS is enabling our customers to manage less and less every single day. So you can take that time that you've saved up to go and do the business mission that you set out to do. And I'm so happy that we have one of those stories that is going to be shared here today about how Samsung SmartThings modernized their data pipeline from a self-managed Apache Spark architecture to a fully managed data streaming architecture using AWS by using Kinesis Data Analytics, which is our managed service for Apache Flink. Jaewon is going to walk us through how this led to them increasing their business value, reducing their developer time, and also reducing their total cost of business. I know you're all as excited as I am to hear, so without further ado, introducing Jaewon on stage. We're going to be hanging out by the stage after the presentation to answer any Q&A. Over to you, Jaewon.
Thank you, Anusha, for the introduction. Hello, everyone. My name is Jaewon Lee, and I've been working for Samsung as the head of SmartThings Cloud Engineering. Today, I'm going to talk about our journey on modernization of the event processing architecture from batch to real-time. The story will start from a brief introduction on Samsung SmartThings and its data platform. And after that, we'll look through the problems we had in the previous architecture and the reason why we ended up making a decision to evolve. Brief walking through the options we considered and which option we chose in the end, as well as how new architecture looks like will be followed. And I will go a little bit deeper about the challenges we should overcome with the migrations as well. Lastly, I'll talk about the impacts on the platform with this journey. Let's get started. Samsung SmartThings is Samsung's IoT platform that supports more than hundreds of millions of users and devices. As a home IoT platform, SmartThings enables users to easily connect and control the IoT devices. As this diagram shows us the holistic view of Samsung SmartThings ecosystem, Samsung SmartThings platform supports 3 different types of devices according to the connectivity. One type is directly connected devices, such as Samsung Smart TV or refrigerators. Most of Samsung appliances belong to this category, and these devices mainly use Wi-Fi for connectivity. Actually, those are the vast majority of the devices in the SmartThings platform. Another type is hub-connected devices that connects to the cloud via hub. Most sensors out there using Zigbee or Z-Wave, as well as Matter-compatible devices, are classified as this type. The other type is C2C, also known as cloud-to-cloud devices that connects to SmartThings platform via partner cloud. For example, if you have Philips Hue bulb in your home, you can control this bulb from SmartThings by making use of this C2C integration. SmartThings Cloud Platform is the backbone of various smart home services and also adopting microservices architecture to provide meaningful values to the end users. As we saw earlier, all data sent by IoT devices will flow through the cloud, and it needs to be processed on a real-time basis. As SmartThings is an IoT platform, and all user experiences are expected to work based on this data. SmartThings data platform takes the responsibilities for this data processing, and it processes around 30 terabytes of data on average every day. With this data, SmartThings data platform provides various features. In the platform, there are two types of histories. One is the history on what happened in devices, and the other is the history on what users get from the devices. All the histories for the last 7 days are stored in data platform. One another feature is usage statistics. Key use case of this feature is to provide users with energy usage patterns or savings of eligible devices. The last feature is analytics plus recommendations. We analyze all the data and get user usage patterns or other meaningful insights. And from time to time, we recommend useful functions as well based on this analytics. This diagram shows how SmartThings data platform looked like in the past. As you can see, in this architecture, we used Apache Spark framework as a data processing engine on top of Apache Hadoop cluster. And all these were self-managed services running on EC2. Here, Apache Spark is an open source framework for cluster computing. And Apache Hadoop is an open source project suitable for distributed computing by making use of the HDFS as a distributed file system. Let's take a look at how it works one step closer. Sensor data from IoT devices, such as TVs or refrigerators, is coming to the cloud through device gateway, which is an endpoint between the device and the cloud. This data typically goes to the Kafka pipeline, which is an open source distributed event streaming platform. Then Spark apps get data from multiple sensors or sources, such like Kafka or Kinesis, and do processing, so-called ETL. All processed data are sent to various sinks, such as database and data lake. The final enriched or aggregated data are stored in database or S3 so that it can be used by other microservices when needed. We are using HBase as a database, which is a NoSQL database for big data running on top of Hadoop and HDFS. At any time when a mobile client requests data through API gateway, the relevant service will query database and get back to the client. So we had 50 Spark applications to handle all different business requirements, and they processed more than 30 terabytes of data on average in a day. But it was on the rise in summer because of the seasonal events. At the very first beginning, everything worked pretty well with this architecture. Over years, however, as the data volume to process has been dramatically increased with a rapid increase of SmartThings users and connected devices, we started struggling with several issues. Let's take a look at what issues we've had and how these challenges affected our platform. Since multiple Spark applications might be running on top of Hadoop clusters with Yarn at the same node on a single EC2 instance, it was very difficult to have the resources reserved to individual applications. So oftentimes, we saw the resource contention among Spark apps, particularly when data ingestion traffic surged. As a result, some of the Spark apps could be in starvation of CPU and memory, and it caused a delay and a performance degradation while processing data, since we didn't have a solution to detect noisy neighbors in place. In this case, we had to increase the number of nodes in Hadoop cluster manually according to the traffic, or had to restart Spark apps in order to recover from failures. Moreover, we spent a significant amount of time to remediate the outage caused by CPU maxed out and lack of memory in Spark apps, because we were not able to use auto-scaling in Spark. In order to leverage the auto-scaling in Spark, we should be able to use both of node level and application level auto-scaling at the same time. But it required to implement additional external shuffling services. These challenges sometimes led us to drop the data accidentally. And after all, it caused bad user experience due to such like the inaccurate device history and wrong energy consumption usage statistic. As a result, it brought about high costly overhead at maintaining workloads in operation. These numbers represent the instant alerts we received in a month, which came from the outage in Spark app. We had to address more than 5 outages on average in a day. When any Spark app goes down, the data won't be consumed in time. And then we'll get delayed notifications. App failure is representing this case, and manual recovery is the case that we have outages in Hadoop because of the failures from Spark components, such like Libby or Yarn. This number tells us, well, how we suffered from the challenges I mentioned earlier. And then it also tells us the reason why we had to retrofit our data platform architecture. I think there is no one-size-fits-all solution, but we had to re-architect our data platform. So we kicked off Data Platform 2.0 project. In this project, we set 3 objectives. It was pretty expensive because we had to reserve more resources than required in order to work well, even though some of these Spark apps go down. So the first objective was to increase the cost efficiency. And also, we wanted to improve the stability and availability of our data platform and to have the operation more efficient. In other words, we had to find out an alternative that would cost less than Spark apps running on top of in-house Hadoop cluster and ensure higher stability with better operational efficiency. So we explored all available alternative solutions and set criteria to evaluate each of them. The main considerations were like this. The alternative solution should be able to processing large scale on a real-time basis. Our data platform is receiving hundreds of thousands of requests per second. So we should be able to deal with this amount of data appropriately. And also, we try to find out a solution which is much easier to maintain the cluster with high availability. So we preferred fully managed solution to self-managed ones because it was too painful to manage infrastructure. And I was also hoping that the engineering team was able to focus on delivering more meaningful business value without needing to bother about infrastructure management. The last consideration was that node and application should be scalable automatically according to the workload. That is, we should be able to use auto-scaling. That's because of the fact that we were not able to leverage auto-scaling in our old architecture, affected the cost and efficiency. Under these considerations, we ended up narrowing down the alternatives to 2 candidates, which were Apache Spark and Apache Flink. Apache Spark operates in a micro batch that collects and processes small units of streaming data, while Apache Flink operates by processing each streaming data on a real-time basis. Without node auto-scaling has to be applied in order to improve operation cost and operation efficiency. Although Apache Hadoop Yarn was previously utilized as a cluster manager, without using Kubernetes will provide better stability and maintainability than using Apache Hadoop Yarn when operating several applications. In addition, cluster usage had to be controlled according to the constantly changing data traffic to lower the system cost, which also required auto-scaling of application. To use auto-scaling of Apache Spark on Kubernetes, which was selected as the cluster manager, the external shuffling service or unstable dynamic allocation had to be used. This was a pretty big burden to go with Apache Spark. Since SmartThings data platform mostly has applications that process data on a real-time basis, we thought it is more suitable to have the real-time data processing model of Apache Flink than having micro-batch processing of Apache Spark. We ended up choosing Kinesis Data Analytics for Apache Flink as our final solution for Data Platform 2.0 because of the advantages it has. At first, with constantly changing data traffic in the IoT environment, being serverless greatly helps in reducing operational human resources, and it is also fully managed solution. And secondly, each application behaves independently, not affecting other applications in terms of using system resources. And lastly, it can periodically create a save point and use those save points to recover in case of a failure. So we can expect high availability without any additional efforts. Although we had to migrate from Apache Spark to Apache Flink, we chose Kinesis Data Analytics for Apache Flink as our final choice because it better responds to the requirement of Samsung SmartThings data platform and can better address the issue of high availability in the long term. So we've got done a POC first for migration with top 3 most data-consuming Spark apps during 100 days and got a green light to move forward. This diagram shows how SmartThings data platform looks like in current architecture. SmartThings data platform mainly consists of 2 parts. First one is the data processing part. You can see upper in this diagram. And second one is the data serving part. As you can see, all EC2 boxes for Spark applications in the previous architecture were replaced by Kinesis Data Analytics for Apache Flink. Unlike the old architecture, the incoming traffic is going to manage the Kafka first and consumed by Kinesis Data Analytics for Apache Flink. Filtered and enriched data is going back to Kafka, and then they are aggregated and stored in database. And the microservices accessing database have been also containerized with EKS. So we can say the operation of the microservices in data platform is also modernized. In addition to the migration, we wanted to improve the CI/CD as well. Previously, we divided the steps into uploading jar on S3 and using Jenkins to download the jar from S3 to register the application on Yarn. However, it had several constraints. So we modernized the workflow like this diagram by combining CI/CD into a single workflow to seamlessly deploy the latest code. When an application code is registered on Git, the CI tool is utilized to start building automatically. After building is completed, the application jar and configuration are uploaded on S3. After uploading the files, the CI tool calls deployment tasks of Spinnaker. Then Spinnaker calls Jenkins job of each application to deploy it. When Jenkins job is running, it downloads the application jar and configuration files from S3. And finally, Flink application is created or updated by using the downloaded jar and configuration files. With this improvement, we were able to apply configurations to multiple applications at the same time and leverage existing Spinnaker-based continuous delivery infrastructure, as well as keep track of deployment history. Although we decided to have migration because Kinesis data analytics for Apache Flink is suitable for the SmartThings data platform, the process leading up to the migration was quite complicated. There were 3 major challenges we had to overcome. First, we should be able to use auto-scaling that changes rapidly according to CPU usage. And also, we should be able to fill the gaps in terms of performance between Spark and Flink. And lastly, we should be able to manage the offsets of the streaming data appropriately. Let's take a look at each challenge and how we got through them in detail. Although we chose Kinesis data analytics for Apache Flink by supporting application auto-scaling, the auto-scaling of the service had some limitations. We could not make changes for Kinesis data analytics for Apache Flink because the requirements for auto-scaling have been fixed and cannot be changed. It can scale out when an application uses the CPU over 75% for 15 minutes, and scale in when it uses the CPU less than 10% for 6 hours. We thought it takes too long to determine scale in and cannot adjust scale out requirements based on application, which led us to build custom auto-scaler. The diagram here illustrates the structure of custom auto-scaler and explains how it works. As you can see, Amazon CloudWatch tracks CPU usage, and AWS Lambda changes the application parallelism value when the CPU usage meets the scale-in or out condition. We are using Terraform to manage these components and scaling policy. So we were able to set different scaling policies for each application by setting the cooldown value for such like parallelism min-max, CPU threshold, and etc. By using this, we were able to set our own scaling policies that suit applications, which can scale automatically to meet the event volume. Thanks to this, ultimately, we were able to reduce operation cost. Kinesis data analytics for Apache Flink uses a resource allocation unit called Kinesis Processing Unit, or KPU. A single KPU provides one core, 4 GB of memory, and 50 GB of storage. When we used Apache Spark, we used Apache Hadoop Yarn and Apache Libby to allocate resources. At that time, we allocated the number of CPU cores and memory that are necessary for each application and converted the number of KPUs to be designated for each application. Also, Kinesis data analytics for Apache Flink has a setting called parallelism per KPU. It determines the number of parallelism per one KPU for parallel execution, which is used to appropriately respond to applications that require many CPU cores. But simply converting allocation for system resources when migrating from Apache Spark to Kinesis data analytics for Apache Flink led to several unexpected issues related to application operation. Compared to Apache Spark, Apache Flink has better performance in terms of general streaming data processing. However, in some cases, Apache Flink had lower performance than Apache Spark, depending on attributes of the application. This required us to implement the follow-up measures. The first one is async I/O. Because Apache Flink processes one event after another, applying async I/O is recommended if interactions with the external system are needed. We applied async I/O considering SmartThings data platform frequently interacts with other microservices to process data. If needed, we are also applying async I/O when writing data on database. The second one is the database batch read and write, because Flink works with a complete streaming data processing method. It processes data one by one, but this could undermine the performance for reading and writing database. It depends on the type of database. SmartThings data platform uses HBase as database, but in case of writing database, there is a significant performance difference between writing one unit of data 100 times and 100 units of data at once. The following chart shows performance test results. We concluded that HBase absolutely requires batch write. Even if memory and checkpoint capacity slightly increased, we aggregated data within the application for deployment. Apache Flink supports two types of window triggers by default. It's time and count. We applied both time and count triggers through which we could control the number of data sent to database to make the number consistent. As we saw in the architecture diagram earlier, data is generally imported using Kafka in SmartThings data platform. However, in some cases, data is imported using Kinesis data stream. If Kinesis consumer library is used to retrieve data in Kinesis data stream from Apache Spark, offset is managed in DynamoDB. But one has to be careful since managing offsets in Apache Flink is different from doing in Apache Spark. Whereas Apache Spark requires a developer to somewhat directly involved in deciding offset storing method, Flink follows deployment of connectors. The table here summarizes how to store the offsets when using Apache Spark on SmartThings data platform and after migration to Flink. Kafka connectors of Apache Flink store offsets in a pre-reserved Kafka topic at each time when a checkpoint is saved. Offset is stored in save point if save point of Apache Flink is used. Applications use the value stored in save points as the highest priority and retrieve the value from Kafka topic when save point is not used. The Kinesis connector of Apache Flink completely relies on save point and does not store offset on DynamoDB. Therefore, a snapshot of Kinesis data analytics for Apache Flink must be activated to use the save point function of Apache Flink when retrieving data for Kinesis data streams. Let's take a look at what impacts we have after addressing the challenges. The first impact is scalability. We applied auto-scaling to all dozens of data processing applications to establish a system that can manage traffic increases, even if the amount of traffic gets 4 times bigger. We also used serverless to not have human interaction involvements for system expansion and reduction, and so successfully reduced human resources for operation by over 60%. As you can see in the chart, the application KPU usage is moving according to the event's traffic pattern, which means the resources for data processing automatically scales in and out dynamically. The second impact is reliability and availability. The issue of operating nodes were addressed by migrating all real-time data processing components of SmartThings data platform to serverless. And we also removed the fundamental cause of cascading failures by configuring independent clusters for each application. So when it ran into an incident, it didn't affect the other applications. As a result, we were able to highly improve the reliability, even though one cluster went down. The last impact is efficiency. Previously, it took more than an hour to recover from an error when directly managing cluster nodes. But we can now recover clusters that are allocated to applications just within a few minutes. As you can see, the number of delay notifications on data processing decreased less than 40%. And we've never experienced app failure recovery and manual cluster recovery case at all after the migration. And also, the total cost of ownership was reduced in spite of the increase of computing resources from 500 to 600 KPU. And we significantly reduced the total operation resources by around 80%. With this efficiency improvement, we can now spend our engineering resources to more valuable work. So I'm very happy that the engineering team is more focusing on delivering meaningful business value rather than spending their resources for routine tasks. Although we've modernized our data platform in aid of Kinesis data analytics for Apache Flink, we are looking forward to small additional improvement. While it took under 1 minute to deploy Spark app in the past, it takes 2 to 4 minutes with Kinesis data analytics. If we can deploy the Flink application much faster, it would be really helpful to get the efficiency better. And Kinesis data analytics for Apache Flink doesn't support using different local level, per logger, and KPU metrics yet. As I know, most of these features are under development by AWS service team, but I hope we can use those as soon as possible. All right, that's all I have for today. Thank you for joining the session. And we'll have the offsite Q&A. Thank you.